Yeah, that's right. Okay, so that should work. So save MIDI. Last.
You know this down.
Yes, because the it basically just saves it here, so I don't have to grab it from YouTube and yeah. And you've got post processing. Yeah, you don't really have to. It's good if you lose internet. You still have this one. You lose Camtasia. You have the other one. So. Screen. Voice on. Let's get the audio. Let's do it next. Samsung. Yeah, it's good. Test, test, test. Test, test. All right. Lecture on a stick.
Yeah, things already.
Thank you. All right.
Oh, I see. It's a little pretty thing. Okay. Most of them don't, yeah, in terms of sound. You hear me? Yep. There you go. Got that. Well, the whole point of it, if it comes with this, you would assume it's going to be it's the whole, I don't know. This seems kind of odd. I don't know.
Well, and then, it's that competition we're having.
USB is weird. I mean, admittedly, that is a sort of a standalone or a niche market now, but maybe not as much as it used to be. But
Yeah, because
most of them are designed to fit into standard, at least a standard 3.5-inch, whatever, 3.5 millimeter, whatever jack or some audio, traditional analog audio system, not a. We can copy it, yeah, or you do it. You'll do it faster. Sorry, I didn't copy it up there. I meant to copy that, but it's good. I forgot that Eric started back. I was like, oh, he's back. It's March. Yeah, I didn't know. I knew he was 3 months. I just wasn't sure. I just no. It wasn't. It was only 3 months. You just get used to not, normal whatever. And oh, maybe Barbara won't show up or something. I don't know. Let's see. Yeah, because now that Jillian's here, she's filled up that office. Yeah, him and Barbara seem to hot swap. Same. Did they hire somebody? Okay. Well, they offered. I know they had narrative. Yeah. Do you know who they hired? Or it was a guy? Okay. Okay. So. Yeah, some more commercial space. It's a system job. It's going to be, it doesn't have to be. I mean, especially to get started, there's a lot of stuff that's just generic. I mean, a lot of the stuff Jason and Joseph and those guys, it just needs somebody who's competent. It doesn't have to be specifically HPC, whatever. So I'll say, yeah, right. Yeah. Yeah, he knows a little more about the standards and the rules and certification. He speaks a little more the same. Yeah. No, that's good. Good. No, we needed it. We were short systems. We have been for a while. It's a good time. So in terms of, yeah, well, they searched for it back before when they put the position up for Mike and Marcelo's job. Those ones they put up that one as well, but then they didn't get any good ones on the assistant on the analyst side. Didn't get any decent, nothing that they wanted to, nothing perspective. They didn't know we were going to hire somebody because of the sake of it. They just there was no true or they wanted to. So. I don't know. Yeah, I did when I got the email. And I signed my life away with my security. I clicked my EULA of whatever, right? Yeah, well, okay. I was tempted to tell Jamie to email them back and saying it's against the union rules at U of T to. Remember when the guys at Kingston did that? So one of the surveys or something was going through, and all the people at Queens, they were told they're not allowed to do any of it because it was against. They found there's some rule. One of their people is a union person, like a hard union person, and sure enough, like we know, there's a lot of stuff in our union rules. It's like if something weighs more than 30 pounds, you don't have to move it. Like we kind of skirt, like even a lot of these, like we work after hours, right? Too, but technically we're not supposed to, right? So if you really want to push, so I'm sure there is probably in all that stuff that we're agreeing to, it probably goes beyond our scope of work, right? Well, you know what I mean? Like, there's a lot of this stuff, I'm sure, I'm guaranteed there's protections. Yeah, I know. So that's what I'm saying. I was tempted to. So this actually happened, I think, in a year ago or something. I remember Chris was like, yeah, none of the guys at Queens would fill out any of this stuff because they were told by that this was totally against their whatever, an anonymization. It was something to do with one of those surveys. It was really generic, but they really did, just out of whatever reason. I remember it came up. Like most of us, I just roll my eyes and whatever, right? But it is kind of a funny, interesting, or well, that's the whole thing about Compute Canada. It doesn't really have much teeth because none of us work for it, right? I know, but I'm just saying, but unless they don't really have a whole lot of. Yeah. Yeah, you gotta have some pushback. Yeah, they came up with them. Yeah. Oh, it's way beyond the scope of, yeah, exactly what they're trying to do. Like, they're overreaching. Just be. MOU or something, not this whole fully inundated, whatever. That's this big of this, not, you don't make everything to be, so for the 3 sysadmins that need to work with that on that one system, fine. But for the 200 other employees that, like, we're never going to touch any of this stuff. Why do we care? There's nothing, I mean, we're preaching to the choir. We can normally get started at 10 after. Okay, so I'm just going to hit record on this, so we're good. Okay, everyone. For those who don't know me, I'm Scott Northrup. I'm one of the other unseen analysts at SciNet. And I'm going to be doing some of the lectures here on which was traditionally our 3rd part of this course, focusing more on the HPC, or the parallel specific components of scientific computing. So today it's just going to be a very overview, I would say, just some of the general concepts related to parallel programming, some of the things that are going to add on, and a few concepts. We're not going to get into much syntax or any real hard details here. This is just meant as a generic overview. The next lecture, Marcelo is going to talk a little bit more about some details about if you have batch serial processing. And then we're going to cover 2 types of parallel programming specifically in this course. One's threading with OpenMP, and then distributed programming with MPI. And I'll talk about some of those. We're introducing a lot of new terminology in here. So if you're not familiar with it, just stop and ask, and I can explain the details of it. You've probably heard some of the terminology, but we're going to talk about that in more detail here. So we're going to talk just high level motivation for parallel programming. I don't think it's too hard of a sell to this group, but why do we want to be bothered? It's more extra work. Why don't I just stick to serial programming? The limits to parallel programming, what are the issues? There's a couple of big key things you'll see that we always harp on, especially when we're working with people that are going to limit or important when you design or program in parallel. We're going to talk a bit about supercomputing architectures, but not that I'm going to get too level in the detail hardware stuff. I can get way off in the weeds about that stuff. If you're interested, and you can talk to us, but this is more of just, there's the reasons why you make certain decisions in parallel programming. And unlike serial programming, which pretty much can be portable across different platforms, the different programming models you choose, whether it be threading or distributed memory, those make it, and how you plan or how big you plan to go, are typically still tuned for the different type of architectures. So knowing a little bit about them is important. And it actually is getting worse, not better, with things like GPUs and accelerators. They're actually sort of still very specific programming for those different models. So even though you can still use most of your standard computing programming expertise from serial programming scientific computing, but knowing a little bit about the underlying architecture or the target of where you plan to go is important to know which decisions to make about how you want to parallelize your code. And we'll talk about how those impact it as well. So why is HPC necessary? Well, this is a key group. You know, basically you have either too much data, you want to run a bigger problem, or it's stuff you can't do with your current computing. Either takes too long, too much memory, too big. So this is what HPC resources are for. If you can't do it on your desktop, you need an HPC resource. And if you want to go even larger or do more parameter studies, this is where these systems come in. You know, the issue is that for most of us, at least some of us older guys anyway, we would, in the 90s, you'd basically just wait, your 18 months and your code would be twice as fast when you buy a new computer. Well, you still get a faster computer when you buy a new one, but you're not getting it because of actual serial processing speed. You're getting it because now it's a 8-core chip instead of a 4-core chip. But if you run the same code, it doesn't run any faster. It might even run slower because we sort of topped out in that sort of space. So the only way to get more performance is actually to change your code or your actual algorithms to use the parallel nature of the structure. And we'll talk some of the reasons about why that's going on. So what that means is there's a big difference fundamentally between serial and parallel processing. And the big thing is concurrency. In serial, I just have to line everything up A, B, C, D, E. Sequential programming, I just think linearly, it's great. Problem with the parallel programming is now I have to actually do that sequential, but do it and also do it concurrently. So I have to break up my problem somehow. Different ways you can do that so that I can actually do similar work by multiple people. It's like having one person's job where they're used to doing A, B, C, D, E, but now I've got, up to 10 or 20 or whatever people I've got. I need to be able to break that job up to do it. Instead of being one long assembly line, I have to be able to find out the parts that can be done at the same time that don't relate to each other. And in some workloads, that's perfectly easy to do, pretty straightforward. But in other workloads where, say, time series analysis or whatever else, where you rely on the previous step, that can lead to a lot of problems in just getting it to work, let alone getting it to work well. Anyway, so the thing is that every new modern architecture from your cell phone to supercomputers now has, at least 2 cores. Most have 8. Modern chips are coming out with like 20 some cores. So even just to do desktop parallel processing efficiently, you're going to have to use more cores. So why parallel programming? Well, as I think we've hit on all this type of stuff. There's a limit to how fast a single computer can go. Sort of like a 3 gigahertz barrier. You can do a lot with that sequentially with that 1 3 gigahertz chip. I mean, we're talking 3 billion floating point operations. However, to do really big problems or to do it faster, I need to use more of them. So I need to sort of divide and conquer that problem. The other reason is I may want to do a really large problem. And there's a limitation to how much disk and how much memory I can put on a single node. So even if I have a really nice desktop, which has whatever, 16 core, 16 gigs of memory, a couple terabytes, very high performance desktop, I can do parallel processing on that machine. What happens if I want to do an enormous data set that's hundreds of terabytes, or a very large grid that's in the billions of cells that I want to calculate on? Even if it's feasible, either take too long or I just don't have enough physical memory in that machine. So then I have to be able to break it up so that I can scale across multiple machines. And that's what almost all modern supercomputers are. Is there a collection of fairly decent servers, but just many of them. And if you do it, if you can actually scale to 2 or 4 fairly well, and you do your algorithms properly, you can scale to n. And that's what we're going to talk about, is how actually to design your program or break it up into a way so that it doesn't, so if I want to run, either if I'm running on 2 computers or running on 100, I could actually use them efficiently so that I don't just get a factor of 2 speed up, I can actually speed it up 50 or 100 times. And that's a very powerful thing. So then it introduces larger problems you can solve, higher fidelity, or do more of them. Maybe it's just a matter of now I can run 50 at the same time. That can be a very good mode to do your work too. So so the question is just people say, well, why is this happening? Look, if we look at Moore's law, and Intel loves to tout this sort of thing. Well, look, we're getting, as manufacturing Moore's law it's been misquoted many times. So basically, people say, "Oh, my computer gets faster every 6 to 18 months." But what it really was intended as a manufacturing thing, is they can shrink the amount of transistors they can put on a die increases. More transistors means, more performance theoretically. So this is still going on to a point. We're at like 7 nanometer now. This is going to top out pretty soon. But currently that's going on. So for this plot, they're like, well, my computer should be faster. Why are these modern architectures serially? I'm running my system here, and sitting there is not really changing anything. I've got more transistors. It should be faster. Well, what kind of happened? Yeah, so this is just describing long-term trends. But it doesn't say that the clock speed went up. For a long time, it did go up. The clock speed actually scaled up with the same rate as the processor count. But it's just, we're actually getting more processors, but we're doing that by putting more cores in the same chip. So if we look at it from this point of view, this is our transistor count. So this is still going up nicely. You can see sort of around 2003, this blue dots here are clock speed. We kind of hit 3 gigahertz wall, and we hit the wall. What happens here is just diminishing returns. If you go faster than that, you can do it, but the energy draw is enormous. So it's super power inefficient at that point. So we don't want to do that, because now we're just sucking way too much power. However, we can use more, because we can do a die shrink and actually use more transistors. So there's the power flat lines as well, and the performance flat lines. So we're getting more, we can actually pack more of them in, but now we're just, the only way that they can do that and that is actually to use more single processor cores in the same package. So that's why this curve is a little more telling than this one, which likes to get, and Intel wants to show that, because they want to say, look, we're increasing, we want you to buy newer computers. And it is a faster computer. However, it's not, your serial code isn't automatically going to work faster. So because we're using more cores, we need to be able to program in parallel. So this idea of concurrency. So we have all these multiple cores, but we need something to do. I have my main sequential code that I've programmed, works great, but I've got a 4-core machine, and it's sitting on one, and then 3/4 of my machine is doing nothing effectively. It's just sitting there. Well, what we need to do is we need to look at that algorithm and find out what can be done independently. What workloads in my series of loops and series of structures going on can I divide or split up and do at the same time? Which parts are most there? And ideally, the order of execution wouldn't matter. If they're completely independent tasks, it makes it a lot more flexible if I can do them at separate times and not involve each other. Because anytime I have to communicate, that's overhead cost. And then also, there are data dependencies that limit this concurrency. I have to synchronize at certain time steps. I have to, certain piece of information, I can't go to this step until I have that piece of data. Now, some workloads are completely independent, and they're easily concurrent. If I'm doing a series of images, I've got an MRI machine, and I've got 1,000 images, and I just want to process them. Well, they're each individual frames. Well, I can just run that same serial code 1,000 times. So on my machine with my desktop with 4 cores, that's pretty straightforward. I just launch 4 of them at a time. As long as they've got enough memory and they're not fighting each other, I've got a 4-time speed up. But not all workloads fit that. If you're doing a typical PDE solution or various calculations, that all have to work on the same piece of data, then you can't just do that, run the same serial code n times, unless you're just doing a parameter set. So this is our, as I just said, diagram-wise, to show that in a parameter study, it's pretty straightforward. All I do is I just say I wanted to run a temperature study on the same model, and I just want to run one at 10 degrees, one at 20 degrees, one at 30 degrees. Fine. I take the same code, write a little script to run all 4 of them, I launch them, and no problem. Now I actually can get, if I run them all at the same time and they're all taking the same amount of time, no problem. So this is just very, very high level, I don't have to program, change anything. Thus we get more done in this case. Pretty straightforward. So we're going to introduce this terminology of throughput. All it really is exactly as you'd expect it to be. It's just the number of tasks divided by the number of time. So if I did these sequentially, say I take 10 minutes each, if I ran 4 of them on one processor, then it'll take 40 minutes. But if I actually can do them all at the same, I can do 4 of these at the same time, and my time stays constant, and I can do them all at the same time. So if you have independent tasks, maximizing throughput is really what you want if they're independent tasks. Does that make sense? Pretty basic concept. What that leads into, though, is this terminology of scaling. If you've ever run at Scinet, or you're going to be running your application, one of the first things we're going to talk to you is how does your code scale? This idea of scaling is effectively how effectively or efficiently does your program use those processors. If you're doing that throughput analysis and there's no communication, they're independent, then you can scale to n as long as you have n variables, right? If I have 100 different parameters to test, I can run them all at the same time, and it scales linearly, which is ideally what I'd like to. If I'm using, can I do it 100 times faster if I use 100 cores? Yes. But in real codes, that's not always the case. There's an overhead. Anytime you're calculating in parallel, the serial code itself is as efficient as going to be. Anytime you do something in parallel, there's going to be a little bit of overhead. And you want to minimize that overhead. That overhead is almost always the communications to go back and forth. So in a strong scaling case, what it means is I'm taking the same problem, and I'm just going to divide it across multiple processors. So I have the same amount of work, whatever, 100 by 100 grid, and I did it on one processor. If I do it on 8 processors, ideally, how much faster would I want it to be? Well, 8 times, right? And so you get what we typically refer to as a linear scale up here, right? And these are like embarrassing or typically embarrassingly parallel jobs. As I said, just divide and conquer. It's embarrassingly parallel because I don't have to do any parallel work. I just have to launch them. And that's the ideal case. But we know in reality, you're not going to get that ideal case. So what we'll commonly do is you don't know this code, you don't know the algorithm, but you've got this inherited from the previous graduate student. You're like, well, you can test this. Relatively straightforward. All you do is you run the same code on one processor, find how long it takes to run it serially. Okay, so for the same grid, the same problem, one processor, it takes 10 minutes, no problem. That's our baseline. Then I run it at 2, 4, and 8 and see how much. And I say, okay, at 2, it takes 5 minutes. Okay, that's good. We're still scaling pretty well. At 8 though, we're taking 4 minutes. Well, obviously there was an issue there. There's some sort of drop off in scaling. And figuring out where that balance is, and it has to do with not just the code, the size of the problem, a lot of different details that will come out during the next series of lectures. So this is the overall concept of scaling. It's pretty straightforward. It's just, figuring out, how close or how far away you are from this ideal case. Okay, so non-ideal cases, this is closer to a real case. You want to integrate some tabulated data, right? So we know the integration can be split into different regions and summed by each processor. We can take, if I have a series of data, I can give you some data, you some data, you some data, and you some data, and you can run that tabulation yourself. However, I first have to partition that data. I can't do that completely independently. I have to know who gets which piece. So I have to add a little bit of code at the beginning that splits up the data. I can do that fairly efficiently. But in the end, I need to tabulate all that data. Say it was sums. If I'm summing the numbers from 1 to 1,000, I can do 1 to 250, 250, 1 to 500, all independently. But at the end, I still need to do a reduction. I still have to add those 4, I have to go to each of you and say, what sum did you get? What sum did you get? What sum did you get? And then add them together in this reduction, right? And that is a workload that has to be asynchronized. You'll have to be done to be able to do that. So if you're faster than him, he has to wait. And this also is not done completely in parallel or completely in separately. And then we get this answer. So this is where we talk about the overhead. This is where, where we would lose the scaling or we have a serial component. Now, in a real world section, as long as I minimize, if this is, say this calculation takes an hour and this takes 2 seconds, you're fine. But if this takes 1 second and this takes 1 second, you're not going to do very well in a parallel environment. Okay, so this is, we mentioned this is the parallel overhead from just splitting up the problem. This works well. So for perfectly parallel for large n, if we take a limit if these get big and these get small, we're going to scale fine. Then this is the overhead that's serial. This is the part that actually is going to kill us. Yeah, so what it means is the amount of work in these individual sections. So if this is very short, right, and this dominates it, say this runs for an hour and this only runs a second, then I'm not really going to care about too much of this because it's only going to happen at the end. Most of the work is done in parallel. Say that's 99.9% of the time. So the scaling is not going to be thrown off by that extra 1 second. However, if this is on the same order of this, say this takes a second and this takes a second, this stays constant. And we'll see that on the next slide where I'll show some graphs of how this actually works. Then we're going to see that even I throw more processors at this, this part stays constant. So I get no benefit from the extra processors. This part stays constant. It's a fixed work overhead. I can't divide it up. The whole point of the parallel processing is I want to reduce the amount of time or solve a bigger problem. Okay, so this is that's what I said. So we're gonna call this non-parallel part is a constant. It's TS. And constants are not our friends when it comes to time because there's nothing I can do to reduce that. That's a fixed work overhead, right? So this has been, so Gene Amidal was an IBM engineer, and he came up with this whole, he tried to, quantify this. He actually came up with this whole terminology. It's fairly straightforward. Basically, it's figuring out the speed up and relating it to the fraction of serial overhead, the constant part. So the T serial here is that's the time it takes to do one job, regardless of what's in it. Just we run it in serial on one processor at that time. And then the scale up, as we talked about, speed up or whatever, is if we divide this by the time on n processors, right? So if this was 10 and this time on 10 processors was 1, then the scale up is 10 and it's linear. However, we know there's this constant in here, this TS part. So if we refactor this as a terms of serial fraction, so as a percentage of that overhead. So as we talked about, if it's 1-on-1, it's 50% overhead. We refactor this equation. We can do this as a ratio of the speed up as a ratio of the fraction, say it's 5% overhead, 50% overhead, and the number of processors. And if we plot that out, or you can just do this, you're going to get this asymptotic point. So if you can actually plot this for 5, 10, 15, 20%, and you can see that whatever components of these, so this one is for 5%, even with a small, it says 5% small, that's okay on a small one, but even on a moderate number of processors, like 16, we're almost down to a point of 50% efficiency. So that small overhead, that's serial, and this is a common mistake new parallel programmers come into, is just like, it's only 5% of my calculation, I'm just going to ignore it. Well, that's okay, and to a point. But if you want to scale this up to a very large number, any serial fraction is going to start to dominate your problem. Because after this goes out asymptotically, it doesn't matter how many more processors it actually will start to flip over. So now actually it hurts me more to run more processors because now I've actually got extra overhead. So all this is really trying to prove is that beware of serial components. Of course, you're going to hit the main algorithm. And the idea being is going back to that previous slide, if this is, this is 1 second and this is 10 hours, probably fine to a point. But you still have to be aware of that. So you have to attack the big stuff. But thinking parallel actually is the whole problem. You want to work at the whole problem, not just the individual components. And this is just a way of, sort of mathematically representing that. Because it doesn't take long, it's even something like a small fraction, this will severely hurt how well you can scale it. Now, if you're just doing a series of batch processing and you're only ever running 8 processors, well, you're still getting 75% efficiency at this point. Maybe that's fine. But if you really want to tackle a large problem and do the hundreds or thousands of cores, this basically has to be very, very, very tiny or non-existent, or you're just not going to get any benefit from it. Does that make sense? Don't worry too much about the math of this. It's more of just the general concept is that serial bad. You're going to get burned by it. Is all it's really going to show you. It's this asymptotic effect. So this is just more. So I just broke it into further. Even if you throw an infinite number of processors at the problem, the code will never run faster than 1 hour since the amount of time the serial part is complete. This is just re-emphasizing what we were talking about, and the idea being is that the serial portion is 1 hour. You can never, even if you drive that other part to 0, that constant is what's going to be your overhead. Once again, overall goal is just minimize the serial portions. You want to, as much as possible, think in parallel how to do that. So scaling efficiency is just, I mentioned it, but it's basically just speed up compared to that ideal factor. So it's just another way of looking at the same data, but it might be a little more easy to think about it. Instead of my scale up is 8/6 or whatever, you just say, okay, that's, or 6/8 at 75%, because that's a more real terminology. 100% inefficiency means I'm doing fine. But it's just a, 1 over that fraction over p, whatever, right? It'll invariably fall off, and that's what all your scale up plots, ideally you want them to look like this, but typically they look something like, if you're doing that, you're doing pretty good. If you're doing this, you're not as good, but this gap here is going to be your relative to this gap, A over B, that's going to be your efficiency difference, right? And we can't get 100% efficiency. I mean, as much as we try, as soon as you have some communication, you can't be as efficient, right? If you're not doing something completely different. All you can do is to try to minimize this portion, that overhead, as much as possible. So if it's 1 or 2%, fine, you can still scale really well. If you minimize that as much as you can, then you're gonna scale relatively well, and that's all your goal is. Because even if you're taking, say if it's not great, say it's still only 80% efficient. 4 processors, even with an 80% efficient, I'm still, say 75%, I'm still 3 times faster than my serial code, even if it's only 75% efficient scaling. It's still 3 times faster, and so that's 3 times faster than I could get otherwise anyway, because there isn't a faster computer. So I don't mean to be totally negative. It has to be perfect scaling to be useful. No, that's not true at all. It's just these are design considerations you should always keep in the back of your head when you're working on parallel. This is the goal, but you're going to have to work there depending on the type of workload or complication you get. So that's sort of the software theory. I don't want to get any more details of that. Just we've introduced the idea of scaling efficiency, speed up, Amadel's law, and the effect of serial components. That general trend. We're going to talk about now and how those apply to supercomputing architectures, how those general sort of parallel programming concepts actually fit into the programming models and the actual hardware that are used in modern supercomputers. So in modern systems, there's really only two classifications now. We kind of listed as 4, but they actually are all a mix of each other nowadays. So the one you're going to come across most is called a cluster, and this is what our standard GPC that we talk about. Any that's basically just distributed memory machines. All it means is I've got this laptop and that laptop. They're separate, running separate operating systems. Don't know about each other, but however, they do share a network. We're connected to the same network. I could get part to run on this one, part to run on this one, and they can work together. Most clusters, to make life easier, the machines are exactly the same. You buy 2 of the exact same servers so that the clock speeds match, they have the same performance, and then if I want to give the workload, it's easy. I just divide it evenly. Okay, so that's called a homogeneous cluster. And really, what makes them stand out a little bit different than just 2 laptops is we usually connect them up with a better interconnect. So instead of just Wi-Fi or Ethernet, we'll use something like InfiniBand or a different type of interconnect. Other than that, they're pretty stock, like over-the-counter type equipment. And that's sort of been dominated the major HPC resources in the last, say, 15 years. The next generation of them is multi-core machines, but now everything's a multi-core machine. They used to have, if you want a big memory, they'd still be you'd have to get these very expensive multi-core machines to handle all that memory. Now everything's a multi-core machine. You can't buy a server with less than 10 or 12 cores in it now. So they have shared memory. So all those 12 cores in that machine can all see the same memory. You log into one machine and you can run it across all those processors. Runs one operating system. but limited number of cores. So there is a scaling limit. If you can only run on that one memory, if you only have 16 cores, you can't go bigger than that. And also, they typically are much more expensive when you get really big. It's way more expensive to buy, say I need a terabyte of memory. To buy one machine with a terabyte of memory in it is more expensive than buying, 4 machines with 256 gig in it. It just is. There's a curve, there's a cost there. Maybe not a terabyte now, it's probably 6 terabytes now, but there's always a cost. So if you can split it up, there's always going to be a price performance balance for that type of thing. So these clusters are really designed to drive flops per watt per dollar, if you want to call it, the cheapest way to get floating point operations. Now, a slightly newer version modification of those is using an accelerator. This has become very in vogue in the last sort of 5 or 6 years. The idea being, they've been around, the idea being, instead of using a general purpose CPU, a regular Intel chip, why don't we leverage other types of chips out there? Primarily, it's graphics cards. Graphic cards are massively parallel processors because graphics is something that's very easy to do in parallel. If I'm doing HD processing, it's 1920 by 1080. So there's 1900 lines there that I can do independently. So a modern graphics processor has, 1,000 individual, very lightweight processors that can do processing very, very efficiently and handle a lot of memory throughput. They're designed for graphics, but if I can leverage my computation in a way that I can use those, I can get a lot more floating point performance per watts or per dollar than I can out of a traditional processor, which has a lot of extra overhead for branchy serial office and operating system type stuff. It's not for free though. They're very fast. So the Xeon Phis or the GPGPUs is like an NVIDIA or an ATI or an AMD. Xeon Phi is an Intel product, which is 60 cores on a daughter card that plugs into your system like a GPU. The next generation will be a native CPU. But the idea being is they're more lighter weight processors, but they're not serially, they're much slower. But if I use a lot of them in my scale well, I can get a lot of performance out of them. But the trick is it's complicated to program. It's either specific languages or I've got to look at my algorithms. I can't just take my code, compile it, and run it. It won't work on the GPU by default. You can't just take a C code and throw it on a GPU. It doesn't work that way. You have to stand on your head a little bit. We'll introduce that lightly in one of the last courses, just some examples of how that works. But it's not a straightforward thing. It uses a lot of the same concepts for parallel programming, but it's not for free. Now, earlier supercomputers, if you go see an old Cray Y1 or an X1, were vector supercomputers. And the way they got performance was instead of doing, A plus B equals C, they would work on A, B, and C being vectors of 128 at a time. So every time I did an operation, I would actually have to vectorize my loops and make them, instead of 4, 1 to 10, or 1 to 100, I would do it from 1 to 10, and then each of those individuals would be doing 10 at a time. Now, this kind of fell off as the top systems, as clock speeds go up and everybody switched to this type of architecture. However, it's still coming in vogue in the sense that on modern chips, in here, they have vectorized units. So they actually have special math units that can do 4, 8, or 16 operations at a time. So if you can find the loops or you find the parts of your codes that can do vector type operations, say you're doing a bunch of 3D calculations that have everything as, X, Y, Z, X, Y, Z, X, Y, Z. The chip can actually do all 3 of those operations within one cycle. So you'll see a lot of terminology by that. SSE, MMX, AVX, AVX2. Those are all just code names from different manufacturers for their vector units. And so even though the machines themselves are still scalar type computers, this vector architecture, the vector algorithms actually even exist in GPUs. The ATI GPUs do everything, because they're designed as GPUs, do everything as vectors of 5 each. So if you want to do everything serial on an ATI or an AMD GPU, you actually only get 1/5 of performance unless you vectorize it. So even though some of these concepts are, the full machines don't run that way anymore, the same ideas come in vogue. Okay, so that's sort of the classification of machines. They really all get mashed together. Most systems are going to be clusters, they're all multi-core machines, and some of them have GPUs with vector units. So even though these are called different classifications, actually all of them exist in any modern CPU, modern system today. So they're not separate, but it is important sort of to pick out the main pieces of them. So the main one you're going to come across is our distributed memory clusters. So this is Ramsey's desk. He still uses an old Apple II his Commodore PET because, you know, he likes green screens and TR terminals. But basically, they're just, as we talked about, take a series of computers that are literally off Dell.com, effectively, and you string them up with a faster network. I mean, there's more to it than that, but we like to say that, it keeps us employed, but it effectively is, that's what it is. The good thing is, from a programming point of view, you can do all the modeling and all the simulation you want on your desktop and transfer it to the other system. It really is the same idea. It's just, you're gonna, especially if it's a multi-core system, you can do everything the programming model, same software, same operating system, everything, and then take it to a system like Cynet, and then you can take that code. It's fairly to a system that you'd understand. It's not completely different like a vector system or anything like that. So Cynet's GPC is an example of that. That's a picture of it. Really just a whole pile of cabinets, 46 cabinets. Each of these has 84 computers into it. And they're just hooked up with a series of interconnects. So there's a lot of them in the machine. So it ends up being, you know, just under 4,000 nodes. The system you guys, this is the system you'll be using. When you log in, individually, they're nothing that exciting. There's each node has 8 Intel x86-64s. They're old, the Halem chips, but they're pretty straightforward. 16 gigs of memory per node, and they run Linux. But the only thing that's really different about them is they run a faster interconnect. Now, you don't have to have that InfiniBand to run your jobs. It's just when you run them on that InfiniBand, it should work much faster than, say, if you run them on Ethernet. So that's an example, and this is what most of the systems you're going to run across are. Yeah. Oh, they're not on campus. It's up north of the city, because this guy sucks a lot of power. So it's offsite, just in a warehouse, effectively. But yeah, the biggest thing is power and cooling. This system at full load is just under a megawatt. So that's our biggest operating cost. And then to cool that, of course, these are all water cooled. I don't know if you can quite see. There's chiller doors here, so they're just to make it efficiency and that sort of thing. But it's an offsite. It's in Toronto, but it's north of the city. So each processor is independent. Programs run on a separate processor and communicate each other when necessary. So this is where that divide and conquer approach really matters. So you have to have a bunch of independent tasks that can run on all these CPUs and only communicate when they have to. And this is where we want to reduce that amount of communication, because every time we communicate, that's overhead. We don't get any work done from communicating unless that's what we're doing is communication networks. Most of the time, the only time we have to communicate is when we need to do those reductions or other problems. So we call these distributed memory clusters because exactly that's the case. This memory over here doesn't see this memory, doesn't see this memory, doesn't see this memory. So I have to explicitly, he has to tell me something. I'm not in his head. He has to actually send me a message and say, this is my number. So I have to do that back and forth. So we have to extend it back and forth. And so the thing is with current programming models, this communication has to be hand coded. I actually have to create a buffer, copy some data, send it. If I was in a shared memory machine, I could just say, oh, here's a pointer, go over there and get it, right? That's great. But in this type of model, this is why it tends to be a little more difficult. I actually have to program that. And when we talk about MPI, message passing interface, this is the programming model that actually is a library that does this, allows it to send those messages back and forth. So in a shared memory machine, it's easier. Now we're in the same machine. We all access the same memory. Now, there's a lot of hardware stuff going on behind the scenes to allow us to do that for coherency and NUMA stuff, but we don't have to worry about that as a programmer at our level anyway. Typically, we'll talk about some of the issues that you can run into, but at least from a diagrammatic point of view, they're all the same. All these processors cores can access the same memory. And then, so each core is assigned to a thread of that individual access, and then we can all access the same amount of data. Any modern system basically uses this now. And you can also use hyperthreading. You can oversubscribe some of these machines as well. So if you only have, say, 4 physical cores, sometimes you can run up to 8 threads, and then that can hide some of this overhead in there too. Typically, OpenMP that is used in this. There are other examples, but in this course, we're going to use OpenMP as a way of doing this. We're programming on this. Now, the limitation on this system is this is a bit easier to program, but this is all I get to work with. If I have a machine that only has 16 gigs of memory or whatever, I can't run a problem that's bigger than that. Or I need more than 4 or 8 or 16 cores, I can't do that. So it's great and it works very well for this size problem, but it will limit how big you need to go. So that's something it's sort of nothing wrong with this. It's just it is not going to allow you to grow as big as a distributed memory system. So one thing that comes up and commonly is confusing in terminology is the idea of a thread versus a process. Right now, when you compile your code and run it, it's a process. It's an independent process. It has its own memory, and it runs by itself. You load up top, and it sits there and runs by itself, no problem. See, they're all individual here. 100% same by itself. Now, a thread, when you're running serially, the thread and process are the same. You have one process. What a thread allows you to do is, if we're running threading, we can take that process and branch it out into a series of children. And each of those children are basically threads. They can all access the same memory of that process. And if we have multiple processes, it actually shows up like we're using almost 800%. They're lighter weights than a process. They're all sort of launched from the same master processor. So here's an example of an OpenMP diffusion code. When you see it running, it just looks as one processor ID, but it actually has, if you actually look underneath the hood, it's actually using 8 threads or more. In this case, it's 8. Whereas when you run an MPI code that are just, they're all individual processes. They can't talk to each other outside the library. The operating system treats them as separate processes. Okay? So those are sort of 2 concepts you have to remember. Is the threads are lighter weight than a process. A process is a full, big, heavy thing. It costs more to start and stop. There's more operating system overhead. A thread is relatively cheap. You can spawn them. You can reduce them. You can create one, do it with relatively cheaply. And so this will come into sort of the programming model. So just the idea, introducing the idea of a thread versus a process. Shared memory communication costs. In a shared memory machine, or the communication costs, we always talk about this is the overhead. This is the difference between clusters, between a commodity gigabit cluster, an InfiniBand one, or a NUMA. This is on memory. And what this really comes down to is the bandwidth on Ethernet is 1 gig. You don't get too much better with InfiniBand. You get much better with memory. These are little numbers, are a little old, but you get the idea. It's more better bandwidth. But what really matters is the latency. This is how much time. If any of you guys are gamers, that type of thing, it's the ping rate. How much time does it send me to send a piece of data and get a piece of data back? Because every time I have to send a communication, I'm probably sending a relatively small amount of data. But that overhead of sending it and getting it back is what's going to cost me, how many messages. So on Ethernet, this is where the big win from InfiniBand is. On Ethernet, I can get away with sending 1 million messages a second or something. But on InfiniBand, these are old numbers now. On new InfiniBand EDR, you can send 150 million messages a second. So that makes a huge difference on how much it costs you to send that piece of data back and forth. And then on NUMA memory, which is this is the communication done on the chip, this is even faster. This is very fast. Still costs, it's not free, but the cost of sending data or sending information, and a lot of time you don't actually have to send the data, it's really just sending a pointer because I can access the same. So the communication is always the slowest part of your calculation, in the sense that every time the cost it costs you to go out and send a piece of data and come back is way more expensive, in terms of relative overhead than that for loop from 1 to 100. And you can measure this. All this really gets the point is that, yeah. Yes, yep. Yep, and that's called hybrid, and we'll talk about that. And that's very, actually you combine all of these pieces together. That's why I said that top slide has 4 different architectures. Actually, in some codes, you're using all of them at the same time. Makes the programming, now I've got to learn lots of different things, but that is very, the ecosystem is very much that way. But this slide here, all I want to point is that as you go up this list, the cost of communication and the effect on your scalability is going to increase. So if we ran on each of these systems, we might have 3 lines like this, where this is the Ethernet, this is the IB, and this one is NUMA. And depending on how big we want to go, the effect of that's going to more dominate our cost. So as he was reading ahead, hybrid architectures, virtually almost all modern systems now, as we said, everything's a big memory node now with multiple cores. Well, doesn't it make sense to reduce the communications? If I'm running a 1,000 core job, instead of, if I've got 8 cores per machine, say it's 1,024, would it make more sense to just run 128 tasks and then have them run threads locally? And the answer is yes. So especially with the idea of hyperthreading. And so we have a Blue Gene system. And it has 16 physical cores, but you can run 64 threads. So if I can reduce the amount of communication remotely, It's always better to send one big message than it is to send 64 small messages, right? So the idea being is I run OpenMP locally, or my thread locally, and then I have a master communicator on the top. So yes, that is a better way to do, but now I have to program two different ways. I got to program a communication stack, but I also have to program the local threading. So by all means, in some of the big codes, that is the best way to get more efficiency. However, I'm offloading the network work or the hardware work to the program. And this is an HPC, that's basically the name of the game. Hardware is as it is. All the efficiency comes from how much work you want to do. Okay? But this is definitely the way. These nodes are only getting fatter. A modern Intel system now has, I think, 18 cores. So you're talking, that's 36 cores per node with 120 gigs of memory. Now you're going to have to go through the same one communication pipeline. This approach is not going away. And then add complexity to that is let's stick a GPU in that node as well. So now I've got a GPU node sitting on a PCI bus with a fat memory node that's got whatever 16 cores that's on InfiniBand. So now I've got 3 levels of architecture. I've got a GPU that I've got to program CUDA for. Then I can thread it locally and then send MPI. So as I said, and this actually has vectorization units in it as well too. So now I've got all 4 architectures that are great, and the hardware guys say, we'll just put them all together. But from a programming point of view, now I've got to take my algorithm that I've designed maybe on a homogeneous architecture that's all the same, and I actually have to be able to put all these pieces together. Now, the point is you don't start doing all of that, but if you really want to squeeze every little bit out of the system, and some of the biggest systems in the world are built this way. Titan at Oak Ridge is a second big supercomputer in the world, and that's exactly how it's built. 18,000 of these nodes, each with a GPU and 32 cores. Right? That's, if you really want to squeeze the performance, that's where they're getting it from. And their next generation is an IBM system built the exact same way, which is going to be really big memory nodes. I think there are 2 terabyte nodes with 8 GPUs in each of them. That's how they've, but the programming model is a mess. It's a lot of work to do that and get it to work efficiently. But this is because the hardware, this is how hardware is getting more performance. We're just having to leverage what we get. And unfortunately, there's a lot of these different ecosystems with MPI, OpenMP, lots of different software. They haven't built a nice unified stack called, New Code X that does all of these. They're coming, but it's not there yet. So as I said, it's really a mix-up of all of these. Now, you don't have to use all of them, right? You can get good performance still building a homogeneous OpenMP code or a homogeneous MPI code, and you can get, for a lot of the work you want to do, that's perfectly fine. However, depending on your specialized work, or you may use a research code that has some of this really put into it, this is out there. Yeah. It doesn't have to be. So that's the good thing is that if you build a hybrid, like if you're using GPUs, it kind of does. If you're using GPUs, it usually gets tailored to like if you're using an NVIDIA, it's tied to NVIDIA stuff. But if you're using an MPI or an OpenMP, it's not. Those are open standards that'll work on IBM, work on Intel, work on Cray. Their compilers will support it. It's like using a C or a Fortran. It's not as portable as that. And the thing is, the balance will matter. So you have to take your code, put it on that machine, and figure out, oh, on this machine, I want to run 8 threads of OpenMP and per MPI task. And on another machine, maybe that's 2 to 1. But the good part is if you've done your code and scaled it to N, then you can port it without too much problem. The GPUs are a little different animal, and even the generation of GPU, you buy a Volta and Fermi, they're all different. So GPUs are their own little animal, same as Xeon Phi. But the standard hybrid stuff, that is fairly flexible. And the thing is, a good thing, if you build a hybrid code, and you want to just use pure MPI, well, you set the number of threads to 1, and you're back to a standard code, right? So, and the good thing is you can do this iteratively. You can start with an MPI code, and then say, oh, I bet you I can get some performance. So let's try to link in a library, an MKL, MathCAD, BLAS library that's threaded. There's no reason you can't do that. But there's a lot of moving pieces, and it does add a lot of complexity. And whether that's worth it, that's going to depend on what you're doing. So you could choose your programming approach. As I said, embarrassingly parallel applications. This is just, you really just script it. And next week, on Thursday, Marcelo's going to talk about that, how to use, I've got serial jobs and I want to just do them efficiently. How do I batch process that? Shared memory, you can use OpenMP or you can use P threads, POSIX threads. It's another way of doing that. We're only going to talk about OpenMP in this course. Distributed memory, the most dominant way to do this is MPI. There are new languages called PGAS, which stands for Partition Global Array. So they're trying to take the benefits of a global memory, and then like in Fortran, you just add an extra index, and now you can access that globally. We have, that's co-array Fortran. UPC is a C variant of that. That's coming up and going. It's not really mainstream yet, but that is, if you're interested in that type of stuff, we actually did a course on that. We have material on that, but MPI by far and away for the last 10, 15 years has been the standard, and it's not going anywhere. So that. And you'll learn that in this course. Graphics, CUDA, OpenACC, OpenCL. This is a Wild West, really is. I mean, CUDA is an NVIDIA specific. These are up and developing. Some of this is being merged into OpenMP now, but it's still very much a non. It's up and out there. And then hybrid combinations. Basically, pick all of them. You can mix all of this together. The good thing is you can mix all these together. They're not. You don't have to pick one or the other. If you want to lay out a GPU in later, you can. They won't fight each other. You have to be a little smart about how you do it, but you can mix them together. You can run MPI, you can even nest OpenMP, you can do all that type of stuff. But it does change left here. I just want to touch the last little bit here before we get done, the computation bound versus data bound. For a lot of simulation stuff, it's almost all computation bound. It's the time it takes to do those, various fast Fourier transforms or whatever. So that's need to focus on the parallel process threads. Different type of computation to do, and the data, you want to bring the data to the computation. Now in data bound problem, that's this data parallelism. You have to be able to split the problem up. I've got a pile of experimental data, pile of whatever, and then I need to dump this down, and then I need to, in this case, you want to bring the computation to the data. These are a little bit different. We're going to primarily focus on computational bound problems, but if you're in the sort of the data sciences field, the data bound problems come up more often. This is just a terminology thing. There's sort of two types of loops of how you do. Fine-grained parallelism is loop parallelism. This typically is your OpenMP. So this is breaking up 4 loops. When we do coarse-grained parallelism, which is usually task, that's divide and conquer, you'll see this more in MPI. These are just algorithmic approaches to how you want to split up the problem. And we'll talk about more of these in more detail when you see the actual, we talk about those next couple of courses. And all this really comes is you have to change the serial algorithm and how you do things parallel, based on which one of these you want to approach. And that's why we went through the architecture and how you want to program it. So you need to learn parallel programming because everything's parallel now. Minimize serial, and there are many types of clusters, but they're all the same basically now. Choose your model. And it depends on your problem. People come to me, which should I use, OpenMP or MP? I'll say both. It depends. I can't tell you that for sure. Okay, so that's enough for today, and we'll get into the details on Thursday. Okay, thanks, guys.
What is the limitation of data processes? So you said that when you're using so okay, I learned yesterday that I was doing and like the code is already started. So does it mean that I should ask him because I don't have